Another day, another story. If a tree falls in a forest and no one is there to hear it, does it make a sound? Perhaps not, some say. Transition to a scientific laboratory with quantum equipment. And if someone is there to hear it, if you think that means it obviously did make a sound, you might need to revise that opinion. We have found a new paradox in quantum mechanics, one of our two most fundamental scientific theories, together with Einstein's theory of relativity, that throws doubt on some common sense ideas about physical reality. Take a look at these three statements. 1. When someone observes an event happening, it really happened. 2. It is possible to make free choices, or at least statistically random choices. 3. A choice made in one place can't instantly affect a distant event. Physicists call this locality. These are all intuitive ideas and widely believed even by physicists. But our research, published in Nature Physics, shows they cannot all be true, or quantum mechanics itself must break down at some level. This is the strongest result yet in a long series of discoveries in quantum mechanics that have upended our ideas about reality. To understand why it's so important, let's look at this history. Quantum mechanics works extremely well to describe the behavior of tiny objects such as atoms or particles of light, photons. But that behavior is very odd. For Niels Bohr, one of the founders of the theory a century ago, that's not because we lack information, but because physical properties like position don't actually exist until they are measured. But that raises the crucial question: what is so special about a measurement? In 1961, the Hungarian-American theoretical physicist Eugene Wigner devised a thought experiment to show what's so tricky about the idea of measurement. In our research, we built on an extended version of the Wigner's friend paradox, first proposed by Károly Bruckner of the University of Vienna. Our experiment goes like this. The friends enter their labs and measure their particles. Sometime later, Alice and Bob each flip a coin. If it's heads, they open the door and ask their friend what they saw. If it's tails, they perform a different measurement. Although a conclusive test may be decades away, if the quantum mechanical predictions continue to hold, this has strong implications for our understanding of reality, even more so than the Bell correlations. We showed that if this were the case, there would be limits to the correlations Alice and Bob could expect to see between their results. We also showed that quantum mechanics predicts Alice and Bob will see correlations that go beyond those limits. All of this does not imply that you can choose your own reality. Firstly, you can choose what questions you ask, but the answers are given by the world. And even in a relational world, when two observers communicate, their realities are entangled. In this way, a shared reality can emerge, which means that if we both witness the same tree falling and you say you can't hear it, you might just need a hearing aid. Thanks for watching.